For years, scientists studying the fault capable of producing the Pacific Northwest's next megaquake have been working with a genuinely unsettling blind spot. The fault sits miles offshore, buried thousands of feet beneath the ocean, in a location so difficult to observe directly that researchers have spent decades essentially guessing at some of its most basic behavior based on indirect evidence and reasonable assumption. Then, a team of researchers took a decade of raw data collected by permanent seafloor sensors, applied a technique almost nobody had used on a subduction zone before, and found something that doesn't match the simple picture most hazard planning has been built around. Part of this fault isn't behaving the way everyone assumed, and the reason why involves fluid moving through the Earth in ways nobody had actually mapped in this kind of detail until now. Today we're breaking down exactly what researchers just discovered hiding along the Cascadia Subduction Zone, why the technique they used to find it is genuinely novel, and why this discovery might mean the fault's behavior is both more complicated and, in one specific respect, potentially less catastrophic than scientists previously understood. Here's why this particular discovery is worth taking seriously rather than filing away as one more incremental academic update. Most new Cascadia research over the past few years has added detail to a picture scientists already broadly understood, refining exactly how big the next earthquake might be, or exactly how the plate is shaped at depth. This is different. This is evidence that an entire stretch of the fault, a segment stretching across the middle of the subduction zone, isn't playing by the same basic rule most hazard models have assumed applies uniformly along its whole length. That's not a refinement. That's a genuine structural surprise, the kind that sends researchers back to reconsider assumptions baked into models people have been using for years. Let's start with the basic mystery that's puzzled seismologists about this fault for years, because it's the exact question this new research was designed to help answer. The Cascadia Subduction Zone runs for more than 600 miles along the Pacific Northwest coastline, from Vancouver Island down through Washington and Oregon into Northern California, marking the boundary where the Juan de Fuca plate is being forced beneath the North American plate. It's capable of producing an earthquake up to magnitude 9, on par with the most powerful earthquakes ever recorded anywhere on the planet. And yet, compared to almost every other major subduction zone in the world, Cascadia is strange in a specific, genuinely puzzling way. Most subduction zones produce a more or less continuous background hum of smaller earthquakes, the sound of two tectonic plates grinding past each other in fits and starts as they slide. Cascadia doesn't. It sits unusually, almost eerily quiet, producing very little routine seismic activity along most of its length, a silence that has fueled the standard working assumption for decades that the fault is simply locked. The two plates jammed together by friction, unable to slip smoothly, silently accumulating stress that will eventually be released all at once in a catastrophic rupture. The problem with that assumption is that it's based almost entirely on the absence of a signal, on what scientists aren't seeing, rather than direct, detailed observation of what's actually happening along the fault itself. And a fault sitting miles offshore, buried under the ocean, is a genuinely difficult thing to observe directly. That's exactly the gap a team of researchers at the University of Washington set out to close, and the tool they used to do it represents a genuinely different way of listening to a fault than anything applied to Cascadia before. Led by Malene Kidawela, a graduate of the University of Washington's Marine Geology and Geophysics doctoral program, working alongside Maureen Denol, William Wilcock, and Quanfu Feng, the research team turned to a technique called ambient seismic noise interferometry. Rather than waiting for actual earthquakes to occur and then studying the seismic waves those events produce, this method extracts information from the continuous, low-level background vibration that's always present in the Earth, the seismic equivalent of static, generated by ocean waves, wind, human activity, and countless other sources that never stop. By carefully analyzing tiny changes in how that background noise travels between pairs of seismic stations over time, researchers can detect subtle shifts in the seismic velocity of the rock in between, changes that indicate the rock itself is being stressed, fractured, or altered in ways that wouldn't necessarily produce a single detectable earthquake at all. It's a genuinely clever way of listening for changes in a fault's underlying condition without needing the fault to actually rupture first to generate a usable signal. To apply this technique to Cascadia, the team needed exactly the kind of long-term, continuously recording infrastructure that simply didn't exist for most of the fault's history. They found it in two connected networks of permanent, cabled seafloor observatories, the Ocean Observatories Initiative's regional cabled array, with instruments positioned at Slope Base and Southern Hydrate Ridge off the Oregon coast, and Ocean Networks Canada's array more than 400 kilometers to the north at Clayoquot Canyon off Vancouver Island. These aren't temporary instruments dropped onto the seafloor for a few weeks and then retrieved. They're permanent, cable-connected sensors, continuously powered and continuously transmitting data back to shore in real time, exactly the kind of sustained, decade-spanning observational record that makes a technique like ambient noise interferometry genuinely possible in the first place. As Wilcock put it plainly, the specific research simply would not have been possible without cabled observatories, a direct acknowledgement of just how much this discovery depended on the kind of unglamorous, expensive, long-term infrastructure investment that rarely makes headlines on its own but quietly enables exactly this kind of breakthrough years down the line. It's worth understanding why this kind of noise-based technique represents such a genuine departure from how seismologists have traditionally studied fault behavior, because the shift matters for understanding why this specific discovery had gone unnoticed for so long. Conventional earthquake seismology is fundamentally reactive. It waits for an earthquake to happen, then studies the waves that earthquake generated to learn about the fault that produced it, meaning a fault that simply doesn't produce many earthquakes, like most of Cascadia, offers correspondingly little raw material for traditional analysis. Ambient noise interferometry sidesteps that limitation entirely by treating the constant, chaotic background rumble of the planet, most of it having nothing directly to do with the fault at all, as a usable signal in its own right. Every time that ambient noise happens to travel between two seismic stations, it picks up a subtle imprint of whatever rock, fluid, and structural conditions it passed through along the way. And by comparing those imprints day after day, year after year, researchers can detect the Earth itself changing in the gaps between actual earthquakes, exactly the kind of continuous, decade-spanning picture a historically quiet fault like Cascadia had never really been given the chance to produce before. Using roughly a decade of this continuous seismic noise data, the research team identified something genuinely striking, a sharp, previously undocumented contrast in how different sections of the Cascadia Fault are actually behaving right now. Northern Cascadia, the researchers found, does behave essentially the way the standard model predicted, a fully locked megathrust, showing persistent, uninterrupted strain accumulation over the full decade of the study, consistent with the conventional picture of a fault silently building toward its next major rupture. Central Cascadia told an entirely different story. In that stretch of the fault, the data revealed something researchers hadn't previously documented in this kind of detail, evidence of what they termed active protothrusts, essentially young, still-forming fault structures branching off from the main megathrust boundary, undergoing slow slip events, and alongside them, evidence of fluid moving rapidly through fault pathways in the overriding plate directly above the megathrust itself. It's worth taking a moment to understand exactly what a protothrust actually is, because the term itself reflects something genuinely significant about what this discovery reveals. A protothrust isn't simply a smaller, less important version of the main fault. It's essentially an embryonic fault, a structure in the process of actively forming as the stress and deformation associated with subduction get distributed across a broader zone rather than concentrating entirely along one single, clean fault plane. Finding evidence that protothrusts in central Cascadia are actively slow slipping, meaning they're gradually, quietly accommodating some of the plate motion through slow, gentle movement rather than everything remaining locked and waiting to release in. One sudden burst represents a genuinely new piece of the puzzle for how stress and strain are actually being distributed beneath this stretch of coastline. The fluid movement side of this discovery is arguably even more significant, and it connects to a broader body of research that's been building for several years around exactly how water and other fluids move through a subduction zone. As the Juan de Fuca plate descends into the earth, heat and pressure squeeze water and dissolve minerals out of the subducting rock, and that fluid doesn't simply stay put. It migrates upward through cracks and fault pathways in the rock above, sometimes reaching all the way to the seafloor. The research team identified specific structures acting as conduits for this fluid in central Cascadia, including splay faults branching upward from the main plate, boundary in a specific structure called the Alvin Canyon Fault, both apparently transporting fluid rapidly enough to represent what the researchers described as genuine fluid highways cutting through the overriding plate. Here's where this discovery becomes genuinely important for understanding earthquake hazard, rather than simply being an interesting piece of subsurface plumbing. The research team's analysis suggests that this fluid movement isn't simply a passive byproduct of the subduction process happening alongside the fault's earthquake-generating behavior. Effective fluid transport through these pathways, the researchers concluded, likely modulates the fault's overall earthquake behavior. And critically, the evidence suggests this fluid movement tends to stabilize rather than destabilize the megathrust, reducing the kind of fluid-induced frictional weakening that can make a fault more prone to sudden, catastrophic slip, and potentially acting as a genuine barrier that could help arrest, or at least limit, how far a major rupture is able to propagate once it begins. It's also worth understanding what the researchers mean specifically when they describe fluid pathways potentially acting as barriers to megathrust earthquakes, because the phrase can sound more reassuring in isolation than the underlying physics actually supports. A barrier in this context doesn't mean a wall a rupture simply cannot cross under any circumstances. It means a section of fault where the specific mechanical conditions, in this case, fluid actively draining pressure away from the fault interface, rather than allowing it to build toward the kind of sudden frictional weakening that helps a rupture accelerate, make it comparatively less favorable for a passing rupture to sustain itself. Ruptures on real faults have been documented crossing weaker, less favorable barrier segments before, particularly when the earthquake arrives, already carrying enormous accumulated energy from a fully locked segment on either side. So while this discovery offers a genuinely plausible mechanism for why Central Cascadia might behave differently during a major earthquake than the fully locked segments surrounding it, it stops well short of guaranteeing that a rupture beginning elsewhere along the 600-mile fault would necessarily stop, or even meaningfully slow once it reached this particular stretch of coastline. This finding deserves to be understood with real precision, because it's genuinely more nuanced than either a simple good news or bad news framing would suggest. The researchers found that Central Cascadia currently sits at what they describe as a locking ratio of roughly 50%, meaning the fault in this specific stretch isn't fully locked the way Northern Cascadia is, but it's also not freely creeping without any accumulated stress at all. It's sitting in a genuinely intermediate state, partially locked, partially released, through the slow, gradual movement associated with the protothrusts and the fluid pathways feeding them, and the researchers are careful to note real limits to what this finding actually tells them. They can't currently determine whether the fluid identified in these pathways is pressurized enough to actually trigger earthquakes on the specific splay faults or the Alvin Canyon fault directly. And critically, finding that this fluid system appears to promote stability during the kind of slow, ordinary background conditions captured over the past decade doesn't necessarily mean these same structures would behave the same way during an actual major megathrust rupture. The researchers explicitly note that these same fault pathways could still become active and behave quite differently once a large earthquake actually gets underway, even if they functioned as a stabilizing influence throughout the calmer, decade-long period the study actually observed. It's worth understanding why finding evidence that a fault segment isn't fully locked doesn't automatically translate into good news for hazard planning, because it's tempting to hear the fault is stabilizing itself and assume that means reduced risk overall. Partial locking, with roughly half of the plate motion in Central Cascadia being accommodated through this kind of gradual protothrust-driven creep rather than pure stress accumulation, could mean this. A particular stretch of the fault has a somewhat different and potentially somewhat reduced capacity to generate the absolute largest possible rupture compared to a section that's fully locked and storing up centuries of pure unreleased stress. But it could equally mean this section behaves as a segment boundary, a zone that influences exactly where a major rupture, starting elsewhere along the fault, might slow down, stop, or alternatively might not meaningfully affect at all once an earthquake is already underway with enough energy behind it. Untangling exactly which of these outcomes is more likely is precisely the kind of question the research team has flagged as the necessary next step, building detailed rupture dynamics models specifically designed to simulate how this newly documented fluid system would actually behave once an earthquake, rather than a decade of quiet background conditions, is the thing being modeled. William Wilcock captured the genuine, honest uncertainty this discovery introduces about as clearly as a scientist can. Finding this link between fluids reaching the shallow subduction zone is pretty unique, he noted, as is the evidence that the fault isn't completely locked the way the standard model assumed. And he was direct about what that means going forward, that researchers need more instruments positioned specifically in this region, because there may genuinely be more going on beneath this stretch of coastline than anyone has previously been able to figure out. That's a remarkably candid admission from a scientist deeply involved in one of the most closely studied fault systems in North America, that a decade of continuous, permanent seafloor monitoring had just revealed a level of internal complexity nobody had fully appreciated before, and that the honest next step is acknowledging how much still isn't understood, rather than overselling the certainty of what's just been found. Alongside Kittiwella's published findings, an expansion to the broader seafloor cabled observatory network serving this region was funded specifically to add more instruments along the offshore cable system, providing considerably more data for exactly the kind of megathrust research this study represents. Wilcock has been closely involved in those expansion efforts, a direct practical response to a discovery that essentially confirmed researchers have been working with meaningfully incomplete information about how this section of the fault actually behaves, and that the clearest path toward closing that gap is simply expanding the density and reach of the permanent instrumentation already proving capable of revealing genuinely new subsurface dynamics. This kind of infrastructure investment sits within a broader research agenda that separate teams are already pursuing in parallel. at a recent offshore observations workshop convened specifically to coordinate Cascadia research priorities. Kidwella's presentation on protothrusts and fluid highways appeared, alongside related work examining the strength of the sedimentary wedge sitting along the subduction zone and a separate investigation into fluid and methane seeps elsewhere along the same fault system. That clustering of related presentations reflects a genuinely coordinated, if still early-stage scientific push to understand fluid movement throughout the entire Cascadia system as a unified problem, rather than a series of isolated curiosities, precisely because researchers increasingly suspect that fluid transport, in all its various forms across different parts of the fault, may turn out to be one of the more significant, previously underappreciated factors shaping how this specific subduction zone actually behaves. The timing of this discovery connects directly to real, concrete investment in expanding exactly this kind of monitoring infrastructure. Alongside Kidwella's published findings, an expansion to the broader seafloor cabled observatory network serving this region was funded specifically to add more instruments along the offshore cable system, providing considerably more data for exactly the kind of megathrust research this study represents. Wilcock has been closely involved in those expansion efforts, a direct, practical response to a discovery that essentially confirmed researchers had been working with meaningfully incomplete information about how this section of the fault actually behaves, and that the clearest path toward closing that gap is simply expanding the density and reach of the permanent instrumentation already proving capable of revealing genuinely new subsurface dynamics. It's also worth understanding why researchers specifically chose the stretch of coastline they did for this comparison, because the geography itself carries real hazard implications for the people living above it. Central Cascadia, the segment where this newly documented protothrust and fluid activity was found, sits roughly beneath the central Oregon coast, an area that includes population centers like Newport and the surrounding communities, while the fully locked northern segment identified in the same study extends up toward Vancouver Island. If Central Cascadia's partial locking and active fluid pathways do turn out to meaningfully influence how far a future rupture can travel once it starts, that has direct practical implications for exactly which coastal communities might experience the most violent shaking and which might be more likely to sit near a natural boundary where a rupture beginning elsewhere along the fault slows down or stops. That's precisely the kind of segment-specific detail that separates a generic regional hazard estimate from the sort of granular, location-specific risk assessment that actually shapes evacuation planning and building code priorities for individual coastal towns rather than the fault as a whole. It's worth situating this discovery within the broader wave of Cascadia research that's emerged just over the past year or so, because it reflects a genuinely significant shift in how much scientists are actively learning about this fault system in a remarkably short window of time. Separate research using seismic imaging techniques recently revealed a dramatic tear in the subducting plate off Vancouver Island, evidence of a subduction zone gradually breaking apart into smaller fragments at its northern end. Other research has explored a possible dynamic link between Cascadia and California's San Andreas Fault, evidence the two systems may be capable of triggering each other within hours under the right conditions. Yet another study revised the estimated depth of the Juan de Fuca plate itself along key segments, finding it sits roughly 5 kilometers shallower than earlier hazard models had assumed. Layer this newest discovery of active protothrusts and fluid highways in central Cascadia on top of that accumulating body of research, and a genuinely striking pattern becomes clear. This isn't a fault system where the fundamental picture has remained stable for decades, while researchers simply refine minor details around the edges. It's a fault system whose basic internal structure and behavior is being meaningfully revised across multiple independent research fronts simultaneously within an extraordinarily short span of time, largely thanks to genuinely new observational technology and infrastructure finally becoming available to study a fault that spent most of its scientific history hidden beneath miles of open ocean. So what should residents across the Pacific Northwest actually take away from this newest discovery specifically? The honest answer is that this finding doesn't provide a clean, simple update to the region's earthquake risk in either direction. It doesn't confirm the fault is safer than previously believed, and it doesn't confirm some previously unrecognized danger either. What it does confirm, with genuine scientific rigor, is that the simple, uniform mental model many people, and even some earlier hazard planning have relied on, an entire 600-mile fault, behaving essentially the same way along its whole length, doesn't actually match what's happening beneath the seafloor. Some stretches are locked and quietly accumulating stress exactly as expected. Others are doing something considerably more dynamic, threaded with active fluid pathways and young, still-forming fault structures that may be gently releasing pressure, redirecting stress, or potentially doing something else entirely once an actual megathrust rupture gets underway. Untangling exactly which of those possibilities is correct, and exactly what it means for how a future Cascadia earthquake might unfold, is now the specific, well-defined question researchers are racing to answer. armed with newly expanded seafloor instrumentation and a genuinely novel technique for listening to a fault that had been keeping this particular secret for as long as anyone had been paying attention. That's the real story behind this newest Cascadia discovery. Not a single dramatic new hazard suddenly identified, but a genuinely significant crack in the simplified picture scientists have relied on for years, revealed by a decade of patient, continuous listening to the fault's quietest background signals rather than waiting for it to shout. Researchers are already building the next generation of instruments and models needed to understand exactly what this newly discovered fluid system means for the region's next major earthquake. And every additional year of data collected from these permanent seafloor observatories brings that answer closer into focus. Stay with this channel, because we'll keep tracking every new study coming out of this remarkable expansion in Cascadia research. And this is exactly the kind of story where the fault itself is still actively teaching scientists things nobody fully understood just a few years ago.